All right, welcome to Machine Learning with Illustrations. This is part two. In the first part, which was really more setup than anything else, what we talked about was how do you organize the data? How do you get it into tables? We talked about ideas like cross-validation and basically everything so that we are ready to now talk about what the actual algorithms are. So that's what we're going to do now. All right, so to get started, what I'll do is let me remind you of the material that was in the Titanic notebook. Generally, when people look at this video, they've already seen that notebook and they're already aware of what's in it. You can actually watch this section and look at it at a later time. But like I said, normally you've looked at that already. And what happened in that notebook, if you recall, is that we had a data set. The data set was all of the passengers that were on the Titanic, or at least a list of passengers from the Titanic. And it had things like, like basically their names and what kind of cabin or what kind of information. And then here's an example of that. So for example, we had the name of a person who was on the Titanic, whether they were male or female, an age. We had information like description about their ticket and maybe how much they paid for it, what kind of cabin, things like this, and even where they got on. And in fact, there's a little bit more things about what class they were in. And an important thing, basically the label that's in here, is whether or not they survived. So if they are on the list and the ones that are marked, one is whether they survived the voyage of the Titanic, which is of course a disaster, and 0 if they did not survive. So in this case, there's 2 on the line here, which did not survive. So we took that data and we put it, and this is what happens in the notebook, we put it into a data table in this pandas data format. And a lot of the code that's in that notebook is about cleaning the data and putting it into a certain format, in particular, a format that we're going to use to use machine learning models. And that format, if you recall, one of the things that we do is we basically take out virtually all of the text that's in it. And we're reducing it to what's mostly a set of numbers, or basically a matrix kind of form of it. And so survived may stay the same, but things like whether you're male or female, that might get turned into a value like 0 or 1, whether you're an age, what your age is, that got turned into buckets. So if you're 0 to 15, that was one age bucket. If you were 15 to 30, that was a second age bucket. So you would end up with a number like 1 or 2, kind of specifying, or 3, basically how old you were, in the data set. And same thing with fair and other attributes. They all basically got turned into numbers. And the label, somewhat here, it stays the same. It's still 0 or 1, whether the person survived or not. And once we had data in this format, then we were able to run a number of different machine learning types of models. And with each one, we used it to predict whether or not, based on the rest of this information, whether a particular person with a certain set of data that's described on this row, whether the algorithm would predict whether they had survived or would not have survived based on that information. And when we did that, this is what we saw. And here, really what I'm doing is I'm just recapping the information that came from the Titanic data set. I'm sorry, from the machine learning algorithms that we ran on the Titanic data set. And so these are all different versions that we ran. If you go back and look at the notebook, you'll see random forest, decision tree, KNN, support vector machine, so forth. You see this whole list of different algorithms, and they operate exactly on that same data set and they'll give you predicted values. And we take those predicted values and we compare them to the actual value of whether that person did survive or did not versus the algorithm's prediction of whether they did or did not survive. And we can find out how many of them were similar or different. And what we saw was that all these algorithms gave us a different value for how accurate they were. So some basic, solid algorithms that people use all the time, like say logistic regression or your basic support vector machine, they gave us numbers like approximately 80 or 83% accuracy in making a guess of whether the person would have survived or not. And then we had a few algorithms that basically did better. And we had some other algorithms that basically did not do so well. So the ones that did better, there's really a trade-off that's going on here. Sometimes you can get more accuracy, like for example, with decision tree and with random forest and with KNN and so forth. But the trade-off is that usually it takes more training time to be able to do that. And sometimes you can get more accuracy, but you're getting this accuracy at the risk of more overfitting. And what that means is it works great on the data set that you've got, but when you show it new data that it's never seen, it may not perform as well, okay? The other version, you might get less accuracy with some simpler or less complicated types of algorithms, and you might also be using less computational effort. Lots of times people find that some of these middle of the road result algorithms are actually very effective. And depending on what you're doing, it may not really be worth using an algorithm that is better or more complex because of these issues that we've been talking about. Okay, so now what we're gonna do is we're gonna look at most of these algorithms one at a time. And the purpose is that we can understand not only what is the code language that we used to call the library routine or the ability to do the prediction with that algorithm, but that you can also understand what is happening inside the algorithm that makes the prediction the way it is. One of the most common types of classification, and one that I showed you that works reasonably well, actually in a lot of situations, is logistic regression. And the way logistic regression works is that it takes this function here, which looks kind of like an S-curve, and it tries to best fit it onto whatever data that you've got so that you can make a partition, and I'll explain it with this example. So for example, let's say you have a bird, and that's what this illustration is about. And this bird is about, is what is called a swallow. And there's two types of these birds. One is called an African swallow, and one is a European swallow. And the African one is basically faster when it flies, and the European one is basically slower when it flies. So if you look at the data that we have here, all of these yellow dots represent the airspeed of different African swallows that were measured. And all of these blue triangles represent the airspeed, which is typically slower, of the European swallow when it was measured. And now what we're trying to do is find a partitioning line where if you said a random bird, if it was faster than this line, we would guess that it's probably the African swallow. And if it was slower than the value, say 2.5 on this line, that we would make a guess or a prediction or classification that it would be a European swallow. All right, so how does this work? Well, what happens is we take this function that looks like an S-curve, and this function could be shifted, and it could be steeper or less steep. But so in other words, like it could be drawn like this, or it could be drawn like this. And there's a couple parameters that would tell you, which would make this graph either move right or left, and would make it basically steeper, less or more steep. And with those two parameters, we basically find what would be an optimal or a really good guess, a very close, close guess of a curve that would best fit. And by best fit, I mean if you take the error, the distance of every point to this line, that it would be somehow the least amount of error. And just as a technicality, that error is measured with a loss function. And this is something that we talked about in a separate lecture. But basically, we're trying to make this fit, and that's really what the computer code does. So it finds a curve which fits well, and then once you have that curve that fits well, usually the bottom represents the value 0 and the top represents the value 1, and where the curve crosses over at 0.1/2, this is where the separation occurs for the classification. Now, that's all basically the theory of what's happening. To actually call that code and have it perform this classification, what you require is only a few lines of code. And this is something that you can see from the Titanic notebook, and this is basically how it was done. So using sklearn, in other words, using scikit-learn, we basically imported a model, a particular one, and we're going to use logistic regression, basically. Now, this line right here, this first line, and I think one thing that's important to point out is there's not very many lines of code here. There's just like 3 or 4 lines of code, and you're able to do this. It doesn't mean that there isn't a lot of code behind these lines when you call these library functions, but just to be able to use it, to make it do these things, takes relatively small amounts of code. Now, we'll just take a look at the example. So this line here that I'm talking about, log reg equals logistic regression, what happened there is only that we created or instantiated an object, and we're instantiating the object that lets you do logistic regression. In the next line, what we're doing is we're putting in all of the data, for example, all of the passenger data from the Titanic notebook, and all of the labels, that's the Y, and the labels are basically whether they survived or didn't survive. If we were doing the example with the birds, and whether they were European or African swallows, then the airspeed would have been in the X train array or matrix or table, and the Y train would have had the labels, which is something like 1 for African swallow and 0 for European swallow, or something along those lines. All right, so you run that particular line to do the fit. So it's the same object dot fit, meaning we're going to run the fit method. And when you do that, this will take, depending on how much data that you've put in with the X and the Y, it might take a little while, it might take half a second, it could take a long time, but it will come back and it will have chosen the parameters that set how steep the slope is and how far to the right or left this whole S curve, this function will be. And once it's done that, then that model, which already has the curve kind of built into it, can now be used for predicting. So if you look at a prediction line, basically you take the same object that you created, log reg, and you use the predict function. And this time we're going to put in values of X, and we're going to get out values of Y that are predicted based on what we learned from fitting the data in the last line. Now, if we want some idea of how accurate these predictions were, then we could do some sort of comparison. And this object, logreg, L-O-G-R-E-G, has another method called score. And in this case, you can put in X, in other words, the data that you want to train or test with, and you can put in the labels that should correlate to that X, and it will itself return to you a number that's between 0 and 1. And it'll be 0 if none of them are accurate. It'll be 1 if all of the predicted values are the same as the Y labels that you put in, and it'll give you something in between there depending on how accurate it was. And we can basically, at the end, find out when we did this prediction, how accurate was this particular model, in other words, how accurate was logistic regression. Now, let's take a look at another one that's just very common, and that's support vector machines. So the way support vector machines work, and we can do this again with another example so that you have a practical idea of it. Let's suppose that you want to classify 2 different types of animals this time. One is sheep and the other one is goat. And this time we've got 2 different features, 2 different characteristics that we're going to use. One is how many steps per day does the animal take? So this is in thousands, but whatever. How many steps per day does either the sheep or the goat walk? And what was the temperature on that day when this was measured? So if you plot them all out, what you find is that the goats tend to be on this side where they are walking a little bit farther, and they seem to be in hotter temperatures when they do this. And the sheep seem to be walking a little bit less, fewer steps, and with basically areas where there's lower temperature. And now the question is there a line, is there a way that we could draw a partition that would separate that would kind of best separate which are the sheep from which are the goats? All right, now the way that this is done, it's actually quite interesting, and we're not going to go into a lot of the math for it right here, but basically the way that you can think of it is that these variables, the steps per day, you can think of it as like x1, and maybe the temperature, you can think of it as x2, and there's going to be some parameters in a matrix called W, and you multiply W by X. And if you said you want to know all the spots where Wx equals 0, what you get is basically a plane. So if it was just in one dimension, it would be a line. If it was in more than one dimension, it's a plane or a hyperplane. And so you basically got a line, and the line would, just hypothetically, it just runs through the origin like this. Now, you can take different values of W, and you could get the line to have a different slope or angle or something like that. So the W chooses all of the X, which make this Wx equals 0 true, or like for the X that make Wx equal to true, you'll get a particular line or hyperplane. And if you take Wx minus b equals 0, what you're going to do is you're going to take that same line, and instead of being like this, running through the origin, you're going to get it shifted somewhere so that it moves away from the origin. all right? And on this line, basically, that's where Wx now equals B. You can think of it this way. But if you look at just what is Wx, what you've got is, this is the spot where Wx minus B equals 0, but all of these points on this side of that plane are where it's, you might say, positive, and the value of Wx minus B on this side are all places where it's negative. So it's 0 through that line and positive on one side of it and negative on the other side of it. And basically what happens is that the algorithm takes all of the points, like say the sheep, on one side, and it considers them to be like a, sorry, like the goats, and it considers them to be like a +1. And all the other ones to be like a -1. And it multiplies it against this Wx minus B, which is either all positive on one side and all negative on the other side. So where you have Wx minus B times the label, which is positive, yi, which would be positive, then all of the values will come out to be positive. And here on the other side, where Wx minus B, where that part is negative, and you multiply it by a label like the sheep, which is negative, then you're also going to get a positive value. The only time you don't get a positive value is when you've got a sheep maybe on the wrong side of the line, or you've got a goat on the other side of the line, on the wrong side of the partition or the line. And all of those points basically get discounted, and the algorithm seeks to find the best line that minimizes the amount of error that you've got. In other words, the amount of points that are on the wrong side, okay? So at a high level, that's basically what's going on. Now let's take a look at it from a code point of view. Before we look at it exactly from a code point of view, actually, I did have something else that I wanted to say, which is a lot of people really like support vector machines. It's a very popular classification algorithm. And the reason why it's so popular is, first of all, it's very robust. That means you can get reasonably good predictions even when you don't have very much data. In other words, in cases where you have sparse data, like basically you have very few data rows, and you might even have a high number of these dimensions, like x1 and x2. You might have, many, many columns that make up all of the x, that make up the different features that you're doing the partitioning on, and you might have very few rows that you're doing it on, and you can still get those few rows and lots of dimensions, and you can still get pretty good results, perhaps better than you can get with other of the traditional algorithms. Now, people do caution that with this algorithm, overfitting is possible. In fact, not only it happens all the time, and if you're going to use it, then you should look at regularization, should use regularization. Like I said, it does work well with sparse data, but what people say is that if you want it to work well on data sets that have sparse data, you also must train it with a data set that is sparse data. Okay, so there's some background information before we look at the code. Now let's just actually look at the code. So just like in the logistic regression case, there's really not much to this. First of all, we are going to instantiate a model. After we import it, we're going to instantiate it. That's where we created the model. we're going to put in our values of X and our value of Y so that we can train it. We're going to use the fit method here. And then as soon as we fit it, that's where the actual hyperplane gets set, the selection of where is the partition boundary. And once we do that, then we can test it with values that either we've seen already or values that we haven't seen before. And we'll use the predict method to basically be able to see what predictions would happen if we put in a value of X, either ones that we've seen or ones that we have not seen. Okay, and again, you can use the score method, just like with all of the partition or all of the classification methods that's in scikit-learn. And so you can put in the training data again, and you can see what the score is. You could also put in values from X test and Y test, because these ones would have been data that the algorithm was not trained with, it had never seen before, and you could get another estimate of how accurate this algorithm would be with the data that you've shown it. Anyway, the code is relatively short, straightforward, and this is basically a quick example of it. Now, sometimes people will use different kernels with support vector machines. So in this case, we're using a nonlinear kernel, but we could also use a linear kernel. So if we wanted to do that, we could create another model, linear SVC, and we would do the same thing. We would do the training using the fit method, and then we could test it by using the predict with some values, and we could see how similar the predicted values are compared to what we were expecting using the score function, and again, we'll get a different number. Usually what people do in this case is that they would try the linear kernel first. They would see if the accuracy is basically good enough, and then you can try the nonlinear kernels, like the Gaussian kernel, like on the last slide. And you can see if you're getting better results. It will take longer. It's more computationally complex to train, basically when you do the fit. And then you can decide whether it's worth the extra complexity or not for you to get what would be basically somewhat better results by using the nonlinear kernel instead of the linear kernel. Okay, now there's another, I'm going to say, very famous classification algorithm, and that one is called KNN, or K nearest neighbor. Now, the way K nearest neighbor works is that, again, you start with a table. And so in this case, the labels that we're going to do are going to be colors. Like, you know, one particular dot is going to be red, and another dot is going to be green, another dot is going to be blue, kind of with this illustration here. There's these points on the table, and each point has, you could say, like an X1 and an X2, and then you basically plot them, and then the labels are that they're red, green, blue, something like this. And what we're going to try to do is figure out if there are regions where you could somehow predict that if a dot was in that region, it's most likely going to be an X. And if a dot was in some other region, would you say that it's most likely to be a green, something like this. And once you find these regions, what you can do is you can take some data that it's never seen before and figure out with this particular dot, wherever it is, would you then predict that it's a red dot or a green dot? It's basically very spatial in this way. Now, the way K nearest neighbor makes this classification is it simply looks at the neighbors that are most close, the closest to it. So, for example, if you were doing what would be KNN with K equals 3, or 3 nearest neighbors, then what you would do is you'd say, all right, I've got a dot. It's in the middle here. And what I want to do is look at the 3 closest neighbors. So the 3 closest, and this is with Euclidean space, just basically how far away are the other dots. I find the 3 that are the closest, and I'm going to take the majority of them as my prediction. So I'll say, all right, well, there's 2 of them that are red triangles, and 1 of them was blue, a blue square. So I'm going to predict that that middle dot was a red triangle because 2 red and 1 blue, the majority was a red triangle, right? So the way the algorithm would work is you would basically go all, through the entire space, pick every single dot in the whole space, and figure out what the nearest neighbors were, and then say, if there was a point that happened to be on that spot, would I guess that it's a blue or a green or a red? What would it be? And then once you've done that, you basically have found regions, and it's kind of like these regions have been somehow identified. And then any particular dot, you could say, oh, that's in this region, or that's in a different region. That other region would identify green, and this region would identify blue. So basically map out and find the regions, and then from there, you can make your predictions. Now, just want to point out that when it's 5 nearest neighbor, say a different value of K, 5 and N, you can get different results. So for example, now if it's 5 nearest neighbor, you'll look at the wider points. So not just the 3 that are closest, but 2 more. And so that would be this one and this one. And now you have 3 blue squares, and you have still only 2 red triangles. And so the majority this time would be blue, a blue square, and you would have predicted now, if it was 5 and N, nearest neighbor, you would have predicted a blue square as that center point, which you didn't know what it was before. Okay. Now, sometimes people hear the term K nearest neighbor, and they hear something that's similar, which is K means. I'm just going to point out K means is not the same thing as K nearest neighbor. K means is also a type of partitioning algorithm, but it is a clustering algorithm. And it's not that I want to talk about K means on this particular slide. I just want to say that K nearest neighbor is for supervised machine learning, meaning that there is actually a label, red, green, blue. K means is a situation where you have all the dots, but there's no labels, and you want the algorithm just to figure out which dots are closest to each other to make partitions, but not actually know what they are. So it's a different problem that it's used for. Okay, so again, K nearest neighbor, supervised meaning labeled data, and it's a way that you can make predictions. Same thing, you should see the pattern now. It's basically, we're going to import the right code, the library from scikit-learn, and we're going to create the model, instantiate the model, K and N. In this case, we're choosing the parameter 3, so it's K nearest neighbor 3, 3 and n. The fit method is exactly the same. We're going to put in x and y. That's what's going to go through and choose all of the regions, figure out which are the blue, green, whatever, however many partitions there are, and then we can do the predict. So we put in a value of x, we're going to get values of y, and we can also use the score. So let's see, k and n score, put in x and y. That would normally give you a number from 0 to 1, so we'll multiply it by 100. It's what we've been doing every single time to get it from 0 to 100, and then, of course, with 2 digits, 2 significant digits. Okay, now, here's another one. Again, very popular, another, very well used, commonly used classification technique. This is called a decision tree. Now, the way a decision tree works, in all these algorithms, I should say, there's always a table view, there's a graph view, and then there's whatever is actually happening in the algorithm. Sorry, if you look at the graph as an example, these are dots. Some of them are blue, triangles. Some of them are yellow, and they're round circles. And they're a question of, did a person attend an event called Burning Man? It's an event that happens in California. And the parameters, the features that we're testing this on are: 1, how old are they, the age, 20 to 60, and what is their income level? And in this case, this is $40,000 per year to $120,000 per year. And so you can see is most people, just visually, you can see most people who made more than $60,000 a year, who were older than 27 years old, who were younger than 38 years old, that this would have been a pretty good box or boundary region to use for your prediction of whether the people would have gone to Burning Man. Now, you can put the same thing into a table. So you can say every dot, person 1, person 2, every one of these dots is a row somewhere in this table. And then you can have a feature like, is the income greater than 61K? 1 would mean yes, 0 would be no. You can have another feature, is the person's age less than 27 years old? So 0, no, 1, yes, they're less than 27 years old. And you can continue this. You can basically make all of the features columns that are all binary, 1 or 0, that says whether or not that feature is true or it's false. Now, the algorithm decision tree does not pick for you the column headings. It does not pick the value 61. It does not pick the value 27. So you can have a number of columns with different features. For example, is the income greater than 10,000? Is the income greater than 20,000? Is the income greater than 30,000? Or is the income between this range and that range? And they'll all show up as true, not true, so forth. The algorithm does not pick those. But what the algorithm does is it tells you which of those columns, is it this column? Is it this column? Is it another column? Which of those columns is a better choice to do a split to know whether or not? Which one gives you the most information about whether the person attended Burning Man, the event, or whether they did not attend? So the algorithm might come out with the feature, is the income less than 61 $100,000 per year. And if the answer is yes, they did not, that they make less than 61, then, so yes, they make less, but the blue triangle means they probably did not attend. And then they can go to the second column, which might be more important, is the age less than 27. If so, then again, they probably did not attend. And you can keep going down this tree and eventually get to a spot where, yes, this person, we predict that they probably would go to that event. Now, what's really good to know about decision trees and this thing is that, first of all, they're fast. In other words, they might take a little bit of time to train. So the training is complex. It can take time. But the speed of telling you the prediction, that part is fast because it's implemented basically in logic, completely in logic. It just says, well, if this is true, then if this is true, then if this is true, it's just if-then statements, then either yes or no. So it's really fast to get your predicted value. Okay, so that's basically how it works. Now, from the code point of view, because we're trying to integrate all these things together, again, it is very straightforward. We're going to first import the tree from sklearn, this model. We're going to make our object decision tree using this classifier. We're going to fit it with the X and the Y as the data. And again, it's just the table. The X values are basically ones and zeros, whether that feature was true or not true. And the Y is the label of whether, say, they attended or did not attend, or whatever it is that you're trying to predict, or whether they survived the Titanic or did not survive the Titanic. And then you can put in a different value of X or the same value of X using the predict mechanism, and you will get out a predicted value of Y. You can also, just like before, use the score mechanism to see with any given two sets of X and Y, whether or not, not whether, but how accurately the algorithm performed. Okay, so that's decision tree. Now, I'm back to this graph, and I'm going to point out, we started off, and I showed you logistic regression first, and we were getting basically a reasonable accuracy. It was predicting 80% of the time whether the passenger would have survived or not survived based on information simply like gender and what kind of ticket they purchased and the other data that was in that table. We showed you that there are some other very commonly used and increasingly complex algorithms. Showed it to you for logistic regression, support vector machine, KNN, and decision tree. Actually, we showed you linear SVC also, which was very close to logistic regression. We didn't really look at these ones just in the examples. Nothing wrong with those. Those are very, they're common but simple approaches. And again, we were getting more accuracy when we had more complexity. It definitely was taking more training time. And we had this risk, the overfitting risk, that maybe we're getting 86% instead of 80% with decision tree versus logistic regression. But is that going to be 80% always? Or is this 80%, is this 86% only for the data that we trained it with? And that is harder to say. So in some cases, we might be using something that's more complex, but in the end, when we use it in reality, we might not be getting the benefit from it. Okay, now let's keep going. I want to show you the one that we did not talk about yet, which is random forest. Okay, so random forest is a lot like decision tree, except that it's really a set of decision trees. And so what you have is, you have your data. This is basically all of the X values in your table. And then you have your labels, Y. In the example we showed you, Y would be whether or not the person survived the Titanic, all right? And what we can do is we can make random subsets. So we might take this row and that row, and we might make a subset of the X and Y. And we might take a different set of rows and make another subset, and yet another set of rows and make a subset. And we do this with replacement, okay? So now we can choose the same rows over and over into these subsets. And with each of these, we consider this one tree. We consider this a second tree, and consider this another tree. And we'll see if we train it with this value of X and Y, then when we show it a random element of data, a row of data, basically show it an X, and we want to get a predicted value of Y, then what would this tree have predicted? It's either going to predict 1 survived or 0 that they did not survive, right? And then same thing, the second one would give us a 1 or a 0. This last one would give us a 1 or a 0. So we have many, many trees, and each one of them is either saying 1, 1, it'll give us an output. We're going to take the majority as our decision. So if we divided it into 20 trees and 15 of them said survived and 5 of them said did not survive, then our selection, then the whole random forest algorithm would have given us a result of 1 survived, because the majority of the trees, decision trees, which were randomly generated trees, gave us a predicted value of 1. Again, this is actually one of the most accurate of all the algorithms. It definitely takes more complexity because you're doing the decision tree many, many times over. And just like all the other algorithms on the spectrum that we've talked about so far, it's that you risk more overfit, and certainly, like I said, it takes a greater amount of training time. But definitely one of the most common of the prediction / classification algorithms. All right, so looking at it in code, same thing. We're going to import the random forest classifier. We instantiate the object with this line. We will use the fit method so that we can provide it X and Y values, which it will then, if you look at the, when we instantiated the object, we chose n is equal to 1,000 in this case. So we are going to be making 1,000 trees. And then when we do the fit, we're going to be running the algorithm on all 1,000 trees. And then when we do the test, we're going to be comparing the results on all 1,000 trees, getting the majority to get the predicted value. All right, so you can, of course, use score, just like in all the other cases, put in an X and a Y, and you can get a value out. Okay, now, at this point, we've looked at all of these. We looked at random forest, decision tree, KNN, all the way down to about here. And we basically showed you that all of these algorithms, to run them, there's really not much code there. It's just 3 or 4 lines of code. They all have a very, very similar structure. The problem is never in just running this one basic set of lines of code. That's easy enough to do. Usually the problem that you're dealing with is much more complicated. It's part of a system. Cleaning the data turns out to be a lot more work than running the algorithm. Figuring out all the elements of the system beyond just the prediction is really a lot more of the complexity of what's going on. And we did not at all talk about neural networks. This is not the class of algorithms that we've been talking about in this section, even though they can be used for classification, just like the algorithms that we showed earlier. But we're going to use a different tool at a later time to illustrate neural networks, and it's basically TensorFlow. I'm going to end this section just by saying that if you look at the Scikit Learn documentation, there is a helpful map that says, depending on what type of problem you have, whether you're going to end up with regression or clustering or classification, and then of these, there's some basic rules of thumb in terms of which classification technique you might consider. And so you can always take a look at that. Again, it's very high level, but just something to be aware of. And then finally, like I said, the machine learning part, it's one small part of the whole larger system. There's a lot more to it, and we want to keep that in perspective as we go through the class and we go through all of this material. Okay, so that summarizes our overview of the machine learning algorithms, and shows you both the code examples and helps you understand what happens when you make those function calls. Okay, so with that, we're done with this section.